video, we looked at Gauss's law. Specifically, we looked at using Gauss's law to find electric flux. But the main purpose of Gauss's law, at least in the context of AP Physics C, is our goal is to somehow use Gauss's law to find electric fields. And the way we'll do this is by somehow finding a way to pull E out of our integral. So ultimately, our goal is to write E integral dA is equal to Q enclosed over epsilon naught. And of course, integral dA is just our total area. So we'd end up with E is equal to Q enclosed over A epsilon naught. And so in order to carry this through, we just need to think carefully about a surface which will allow us to carry through this operation. And the key to choosing an appropriate surface is to utilize what we call symmetry. So what do I mean by symmetry? Let's consider a simple example, namely a point charge. If I were to stand a distance r away from my point charge, it doesn't matter if I'm at an angle of 0 or at an angle of pi over 2. Nor does it matter if I'm behind the charge or in front of the charge. I expect the magnitude of my electric field to be constant anywhere a distance r away. The shape formed by this is, of course, a sphere. So I expect that if I surround my point charge by a sphere, my field should be constant. And so we'll call this, or so let me draw the point charge at the very center, or as close to it as I can. We call this symmetry spherical symmetry. All we're saying is if I move along a sphere which is centered on my charge, I do not expect the magnitude of my electric field to vary. Note that this isn't only true for a point charge. For example, this would also be true if I had a charge which was solid with radius r. And it would be true whether I was inside the sphere, right? I can draw a radius lowercase r, which is less than capital R, or if I were outside the sphere. I expect that so long as I stay a fixed distance from the center, my electric field should not change. And this will also be true in some slightly more complicated scenarios. For example, I can have a charge density that varies with position. But if the charge density is a function of radius, I still expect to see spherical symmetry. So why all this discussion of symmetry? Again, our goal is to take E out of our integral. And so if I'm trying to find the electric field of, for example, a point charge, I'm going to choose a Gaussian surface, which is a sphere. So I'm going to denote this as our Gaussian surface. And we'll now try carrying through the integral E dot dA. So to begin with, integral E dot dA. As a first step, we need to get rid of the vector notation here. So let's think about the direction of dA. As we said, once we're dealing with a closed surface, we have our dA, which is a small patch of area, with the direction being the outward normal vector. So this will be dA vector. Now, we also know that for a positive source charge, the electric field points outwards. So I know the direction of E as well. And this will be true wherever we are on this surface. E points radially outward, so does dA. And for that reason, we can say, well, the angle between them is 0. So integral E dot dA reduces down to E scalar, dA scalar. And we can write cosine 0, but of course, that is just 1. So I'll get rid of that. And now, as we just discussed, the electric field is constant all along this surface. It does not vary depending on angle. It only varies with r, and r is remaining fixed. So I can pull out my E. Finally, I can say, well, integral dA is just my total area. But we know the formula for the area of a circle, or a sphere, more precisely. So area is 4 pi r squared. Great. What I want to point out is this computation that we just did is the left-hand side of Gauss's law for any of the 3 scenarios that I've outlined above. It's true for a point charge. It's also true for a solid sphere. And it is also true for a varying density. And so now we want to consider the other side of Gauss's law, namely Q enclosed over epsilon naught. So let's begin with case one, where we have a point charge. There, Q enclosed is easy to compute because it is just our entire charge. So we have E times 4 pi r squared is equal to Q over epsilon naught, which we can solve for E. And this tells us that E is equal to Q, like that lowercase q over 4 pi epsilon naught r squared. And as you may suspect, I did not define this in the last video, but there's a relationship between k and epsilon naught, and it is indeed that k is equal to 1 over 4 pi epsilon naught. So what we derived here is just the field of a point charge in the original form we saw it as kq over r squared. What about case two, the solid sphere? So let's begin with the case where r is greater than big R. In that case, notice that all of our charge is still enclosed in our Gaussian surface. And so we get the exact same result. E times 4 pi r squared is still simply equal to total charge over epsilon naught, which gives us the same result as before. But what if we are within the charge? This is where things get more interesting. So our left-hand side of Gauss's law is still E times 4 pi r squared. That has not changed. Symmetry is still the same. But we now need to consider what Q enclosed is. And there's a number of ways to do this. We'll start by doing this without calculus, and we'll then move on to seeing the calculus approach. So here is my charge with a radius capital R. And I would like to know how much charge is enclosed within a smaller radius, lowercase r, contained within the sphere. We can start by introducing a density and say that the density of this sphere is my total charge over my total volume. So capital Q over 4/3 pi r cubed using the volume of a sphere. And therefore, Q enclosed is simply going to be equal to our density times the volume enclosed. Of course, the volume enclosed is just 4/3 pi lowercase r cubed. And so we see a fair bit of cancellation there. We end up with just Q times little r over big R cubed. Okay, so now that we have the charge enclosed, we can now say that E times 4 pi r squared is equal to 1 over epsilon naught times Q r over big R cubed. And we can go ahead and solve for our electric fields. We have Q r over 4 pi epsilon naught r cubed. And so unlike our previous field, which was decreasing as 1 over r squared, this is actually a linearly increasing field. Finally, case 3, we have varying density. And we'll leave this case for our next video.